Yeah, thank you, Andrew. Ну, вообще, я так понимаю, что здесь все по-русски говорят, поэтому я, наверное, буду по-русски рассказывать. Или лучше английский? Okay. Okay, then I'll be presenting in English, no worries. So the first question for those of you who are not working in Yandex would be, what is YT actually, right? So YT is a distributed storage, a computation platform, and the building blocks for the future, for our future. The purpose of this talk, so the reason why I'm here is to share our design decision, how we build such a distributed system, to show some problems we have encountered and show how we going to solve them. So first of all, I would like to ask a few questions. Please raise your hands. How many of you are aware of what MapReduce is? Okay, and how many of you use this MapReduce ever, at least once, have ever used MapReduce? Okay, and how many of you tried to build some kind of distributed system to either implement MapReduce paradigm or either to coordinate some systems? Okay, a few of them. Well, then I would like to congratulate you that for the most of you, this talk would contain something interesting. So the outline would be the following. Firstly, I'll cover the historical perspective on how the YT project has begun. Then I'll describe some current design decisions and our overall architecture. And then I'll proceed to the future plans to describe where we go in the next few years. So for historical perspective, well, Mihai did a great job telling you on how data-intensive parallel systems are built and used, so I will quickly glance across this section. So just to recap, MapReduce paradigm is all about splitting the data into small chunks, applying some kind of mapper to the data, and then regrouping it by some special key and running a reducer all over the data partitions. So usually MapReduce runs on a cluster of hundreds of machines. The data is stored in some kind of distributed storage, which allows you to easily partition data and to append data to a single entity on a parallel. And the first actually mention of the MapReduce paradigm was in 2004 by the Google paper by Jeffrey Dean and the company. And actually first Yandex internal implementation was born in 2006. So Hadoop, for your information, had a first public release in 2007, and it contains some kind of different design decisions. So I will be covering this in more details during my talk. And the YT project started in 2011 and was dedicated to solve some of the scalability and design problems which became obvious during the operations of the current internal implementation. So what were the issues which had given a birth to the YT? So one of the major concerns of internal implementation was the reliability of master server. So if you're aware to an extent how MapReduce works, it contains a master server which coordinates all the other worker nodes, which stores all the information, how the data partition it across the cluster and stuff like that. So both current historical implementation and both Hadoop share a single point of failure in this master node. So we call it master, Hadoop calls it a name node. So the failure of this node leads to a downtime for an hour, for example, for a cluster. Well, second, the historical design of Yammer of Yandex MapReduce had a joint master and scheduler process within a single machine. So eventually, as the data grown, this led to the huge memory consumption, which is currently at 200 gigabytes per machine, per master machine, which is not really scalable. So there was an intention to separate these two processes to the separate machines in order to gain some scalability. Well, actually, the internals were also kind of convoluted and used different mechanics how to store the data. And eventually, there were a few completely different mechanisms how you can distribute blocks of data across the cluster. For example, how you distribute the actual data which you process, like logs or clicks or whatever, and how you distribute the user code, the user application. And this was quite inconvenient because you have a duplicated logic and you have to debug it in two places, and that's not convenient, really. Also, another problem which was not obvious at the beginning was the lack of the extended meta information and introspection capabilities. In order to understand how the system works, how the distributed system works in particular, you have to collect a lot of data in order to measure and analyze what's going on. Because when you have hundreds of machines, you cannot go to a single one to evaluate the slowness. Well, the most hard problem to solve in distributed computing is when someone says to you that something is slow. So you really have to know what to measure, where to measure, and how to measure in order to overcome the slowness. And the other design problem which arose was inflexible resource allocation. So both Hadoop and Yammer share the idea that a single unit of job allocation would be a slot. So slot is it's a non-physical quantity which you declare that you require to run your operation. So usually you declare that you have, for example, 10 slots in a single machine, and this means that this particular node can run 10 instances of user code. And that does not really correspond to the reality when the limiting factors for your computations are memory and CPU. Well, and another problem which eventually arises in every big company that a code bloat arises and some effort have to be taken to maintain it. So there is an open question why Hadoop was not chosen at 2011. So main reasons were, first, lack of understanding how we would solve the same problems in Hadoop, for example, the single point of failure in name node. Well, the more important reason why we decided to go for re-implementing MapReduce is about having the compatible data model. Well, Hadoop will have its own opinion on how to do distributed things. I will cover this in more details when I will go through the design. But this all led to high migration cost, that a total switch to Hadoop would incur a lot of effort dedicated just to moving, and that would completely freeze production processes for a while. Well, and actually, there is a third point on the slide about the cross data center stuff. Like 5 years ago, data centers were not large enough to hold tens of thousands of machines. And this was a scalability problem because you could not afford to have more than 1,000 machines per MapReduce cluster per data center because of the physical constraints. And there is an open question which is not yet solved in some well-acknowledged manner, how to distribute computation on cross data centers. So as far as I know, for example, Facebook, who uses Hadoop quite a lot, they do not tackle with that kind of problem because they just built a huge data center. Well, since we have a few data centers built already, we have to somehow manage this and be able to scale to a few data centers. So to be honest, multi-data center is currently work in progress and it's not finished, but I will cover how we will evolve to this direction. So in 2011, the design goals mainly were better availability and better scalability in order to accommodate the data growth within a decade. And actually, one of the non-primary goals, but an important one, was to build some building blocks in order to replicate the knowledge about the distributed system to the other part of the companies. Well, as Mihai, for example, mentioned, the problem of distributed consensus and the problem of how to replicate services quite complicated. So I'll get to that when I'll describe how we manage this. But if you ever heard about the word Paxos, you probably know that implementing Paxos is not a pretty good thing. So that was our design goals at 2011. So any questions at the moment? Okay. Then I'll briefly cover our current architecture. Mainly, I will state main design concepts we use to derive our architecture, and go on through the major part of the system, such as metadata, the table storage, and the job scheduling. So firstly, I'll talk about the, oops. Oh, there's something weird with the points. Okay, the first topic is about the concepts. So a really good question to ask you when you start designing a distributed system and start thinking about how to engineer it is to ask yourself the question how the cluster would look like. So usually, well, for example, if you apply for a data analysis job, you come to a job, to the office, and the boss tells you, please compute something. You're not thinking about that you have hundreds of machines which are capable of doing something. You're thinking of, hey, where should I get the data? So where the data is stored, how can I run my code on this cluster? So firstly, you have to understand that there is kind of namespace which should be containing all your data, where you can, so you can access it in order to run some computation. And actually, a good distributed computing system would hide all the fault-tolerant related complexities within itself. So you will not even know that there are some failures going on. So all the possible failures would be handled transiently, so you will not mention it. And it is also important that this namespace, its state and its view for you should be consistent, and it should be highly available for you, because if it's not consistent, it would sacrifice your user experience. For example, you start some operation, but you don't know when it finishes, and when it finishes, you will see some chunks of the data, but not the entire result. So this would be an inconvenient, and you have to build synchronization on your own on top of the system. So this eventual consistency thing is good when you deal, for example, with serving some advertisements or some images when the updates are quite irrelevant in time. But when you compute some stages of, for example, machine learning computation, you have to be sure for that particular moment everything is finished and committed to some state. And the availability is kind of a problem for distributed system, because as you may know, the KAP theorem tells you that either you sacrifice consistency or availability or partition tolerance in the distributed system. So since we are working in data center, the network partitioning is not an issue at the moment. So at least within the data center, we decided to stick with the consistency and availability to provide a better user experience. Well, and also a cluster would provide you an interface to actually run something and to do something. So you would like to run some distributed computation, like, for example, a run of fitting the linear model or whatever, or analyzing user logs. You would also like to load and store some usually small chunks of information. For example, when the fitting of your model finishes, you would like to download the model and evaluate it locally for some reason. And usually, if you are working in practice, you have to worry about the metadata, on how do you label the data, how do you manage it in order to build some reliable process. Well, for example, there is a system in Yandex which works, which predicts user behavior on sites to improve quality user of search or advertisements. And there is a cycle of data refresh within the system. So in order to make it run automatically, you have to have a metadata store, so you can mark that, for example, user behavior for 7th of February has been completed. User behavior analysis for 7th of February has been completed. Well, and the question where to store metadata is usually tackled on a separate manner. So a lot of systems use Hadoop separately, for example, from MySQL, in order to store something like metadata in MySQL in reliable fashion and in consistent fashion, and use MapReduce to crunch the big data. Well, it also worth a little bit of discussion what data, metadata, and computation is, because it affects on how you design your system. So the data for the designer of distributed computer system is just bytes, right? So when you, as a data analyst or a data science, work with the data, you think of user clicks, of user IDs, of search queries, or stuff like that. But for the distributed system, everything is the same and everything is bytes. So we decided to store data in tables, and I'll cover that in the next slide, I suppose, on the reasons why we decided to stick with the tables instead of the files in Hadoop. So the metadata, it's hard to describe what the metadata is, but usually it's a convenient manner on how you structure your data, how you access it, and how you store additional attributes associated with the data nodes. So we represent metadata as a tree-like structure where your particular tables are leaves, and there are some attributes associated with either leaves or intermediate nodes. For example, a common structure in our cluster nowadays is a folder which called, for example, access logs, where you have a lot of tables named by the particular day, for example, 2013, 02, 03, the 3rd of the February. And there are extra meta information associated with that table, for example, number of records, the data size, the ID, the unique ID, or whatever user wants to store around. Well, and the computation is an easy part. Computation is described the map reduce model, so usually you provide some kind of mapper, some kind of reducer, and the system rearranges the data in a manner which would be which is required for the computational model. Well, I would like to, in particular, deal with the first point about why we store the data in tables and not in the files. So files are not first-class citizens in our system. So we support the notion of files, but we use files to store, well, files you have on a notebook, on a laptop, for example. Because, well, my personal view is that files are bad abstraction for distributed computing for several reasons. Well, firstly, when you think about the data as a data scientist, you're not thinking about it, hey, I have a file here with a lot of bytes. Well, you usually think that you have a lot of search queries and you have to somehow work with the words within these queries. You somehow to extract, I don't know, entity text or part of speech text from those queries. Or you have to analyze advertisement logs to compute some statistics, to crunch some numbers or whatever. So files require you to deal a lot with serialization and deserialization logic, which is quite inconvenient when you would like to run a few experiments quickly. And actually, when you have a scale of few terabytes, when your data compounds for several terabytes or even petabytes, it's not obvious how you should store this data. So either you should use a lot of files or you should use a single huge file. So in fact, if you would look on Hadoop implementation, Hadoop uses the notion of files, but usually when you provide an input to your operation, you provide a whole directory of files. And one of the reasons why you're doing this is because the output is a lot of files. So somehow the question of how you partition the data becomes separated, become intertwined, become tangled with the question how you store the data. So that's not looked like a cool solution for us, so we decided to stick with the tables. And the last reason, but also an important one, why the files should not be used in distributed system, because maintaining proper POSIX semantics is quite hard. So POSIX semantics tells you that you can do a lot of stuff with the files, like you can do in your notebook. But on a notebook, you can do stuff like locking the files, modifying a few bytes within the file easily, because everything's stored locally. While in the distributed setting, you have a lot of replicas, and you have to update them in a coordinated manner. For example, when you commit an update in the middle of the file, this update should be propagated to the other copies. And that would incur extra consensus decision on these updates, so which is costly, actually. So I actually think that files are merely an accustomed way to think about how you store your data. I think one of the reasons why this notion even become popular in computer science is because when IT technologies emerged, one of the selling points for the managers were, hey boss, you have a lot of files on your desk, like here in the picture, and you can store them in computers, so that would be good for you. And actually, I would like to put another quote over here, a quote by Henry Ford. So if I had ever asked people on what they wanted, they would say me that they want faster horses. And in fact, this strictness of thinking prohibited people from thinking about the automobiles. So we decided to build another primitive on how you store the data and to choose the table as the first-class citizen. So table formally is a list of rows, where every row is just a named tuple. So named tuple means that for every particular, that you have a set of pairs, key and value. Well, for example, there could be a table with 4 rows, like 4 rows with timestamp data with the user field, with the hits field, and occasionally the last record have a special key written lecture equals to 1. So we do not enforce any schema in our table structure, which is quite useful because otherwise this would incur extra schema changes all of the time. So a takeaway from this particular slide, so I can ensure you're not falling asleep, is just if you had a lot of files, please consider making them in a table. So this is quite useful. And actually, if you think about the link language which Mihai was talking about, the link language operates with collections, which are not files. And actually, it's quite good choice of interface because it allows you to separate the ideas on how you transform and compute all of the data and the ideas how you can store and manage the data. Okay. So if you have any questions to the moment, it's a good time to ask. Okay. Okay, question. Once again. Well, it used to be an abbreviature for Yandex tables, name it similarly for the big table, but eventually we got rid of this notion, just abbreviated to the YT. Okay, so then I will follow on the component overview and in particular cover how the cluster is structured, what are the implementation problems, and what are the implementation decisions. So physically cluster is a set of nodes where every node plays some role. There are 4 roles in our system at the moment, which are namely master server, as scheduler, and node service, and a proxy. So if you're to an extent aware of how the Hadoop, for example, is built, you should right now understand approximately how the cluster is built. Well, for those of you who are unaware of how Hadoop works, I will cover it briefly. So proxies are the API endpoints. So they are the points where the user actually interacts with the system, and actually all external I/O goes through them, and all the comments issued to them, and also the authentication performed at the proxies. So they are like a booth serving you when you work with the cluster. So nodes are also quite simple things. They just store data, execute your jobs which you would like to perform, and they strictly obey to the master and to the scheduler. The most interesting and the most important thing of the system, as you may understand already, are masters and schedulers. So, masters. Well, how would possibly the distributed storage work, right? If you have a lot of nodes. If you have a lot of nodes, every node could store a small chunk of data, right? And there should be some point in which you can understand where the data is actually stored. For example, if you're asking for the first 10 rows, you should be able to answer the question where you should go to get them. So this is a responsibility of the master to answer queries on the physical location of the data. So when you query master where I can get this particular chunk of data or this particular table of data, it answers you with the address of the node. It also helps you to decide on which node you should upload your data when you're about to write something. And during this process, master also ensures that the data load across the nodes is more or less uniformly distributed. Also, master handles such maintenance tasks like tracking which data is under-replicated due to machine fault or which data is over-replicated due to machine recovery, when we should issue an extra replication request, when we should balance some things from the node due to high load or stuff like that. So these functions are mainly about how you can manage all these pieces of data on the clusters. But that's not the most important thing. So this is just more or less technical things, but it's important to say about this because this chunk management, it takes a lot of memory actually from the master. So currently in our installation, the master consumes about 20 gigabytes of memory, and the majority of this memory consumption comes from the chunk management. The most important thing for the user is actually the namespace. So when you come to a distributed server asking where my table is located, you're not asking this in terms of chunks of data, right? You're asking in terms of names, like if I have a name of access log, where I can get it. And we built something called Cypress. Well, Cypress for the evergreen tree, because evergreen is somehow associated with high availability. So Cypress is our way to store the metadata and to provide the namespace for the user. And actually, there are some good and great properties of this thing. Namely, every addressable object in the system could be reached via the Cypress. And this is quite valuable, especially for the developers, because at every moment you can look within the system to understand what's going on, to query for the properties of this particular objects like chunks or whatever. And actually for the users, there is another feature which is valuable, namely the multi-version concurrent control. Usually for you as a developer, it's quite convenient to reason in terms of transactions. Like I start a transaction, I write some data, I do some operations, read some data, do some another operations, and then you commit transaction if everything succeeds. And there is always a trade-off on who would manage this consistency, right? So if you're working with key value storages with eventual consistency, you should manage this consistency on yourself. But for the increased velocity of the experiments, it's quite convenient to have transaction management and version control on the server side. Because in this case, you could just issue simple requests like start transaction, and you get an isolated environment for an execution. Well, the objects which I'm referring to are constitute of the two major parts. First part of the objects are namely data structures like scalar values, maps, and lists. And the other part of the objects are specific to distributed computing. They are transactions, logs, chunks, chunk trees, and also the users, the groups, and the accounts which are used within the system to authenticate users to compute the quotas are also the object of such a system. And the most important property which makes this Cypress valuable and actually non-trivial to implement is the requirement of high availability and consistency. Right. So before I proceed in how we implemented the Cypress, I will cover some briefly use cases. So our users currently use Cypress as the substitute for the file system. It's quite convenient for them to think of files, of tables as the files, and for the maps and directories, but in fact, Cypress is more than a file system. For example, with the Cypress, you can make a distributed log service. In particular, we use this ability to coordinate the schedules in our system. For example, the scheduling in our system is done entirely by a single machine. And the second machine in the system acts like a hot stand for the scheduler. If the first instance falls, the second one will substitute it in performing the obligations. And both of the schedulers coordinate with each other through the Cypress. So one of the instances takes a lock on a specially named node, and the other one sees that there is a lock taken, so it does not do anything. Also, it's quite convenient to use Cypress as a highly available config store. For example, proxies, which are used to provide user interface, store their behavioral configuration in the Cypress. They query the Cypress on should they be performing data-intensive workloads or not? Should they be performed only comments or not? Should they stop issuing any requests or not? So this coordination and configuration is done entirely within the system, and this is quite convenient. But there isn't always something you pay for those qualities. And in fact, if we are speaking about scalability, the current amount of data we can store in Cypress is limited by the amount of memory on a machine. We have plans how to shard this meta information, but that would be a non-trivial system to implement. So we are looking forward to implementing it, but it's within our plans, so it's not currently implemented. And I think I'll briefly cover it in the future plans section. Why there is an outline? I see. So I would like to take a few notes how we actually implemented this Cypress. So in scientific community, there is an understanding that a reliable service could be made by the replicated state machine primitive. So you can model your service as a state machine which receives some external actions, modifies its state, transitions to another state, and maybe issues some response back to the user. The way how you can make this service available is through replication. You just keep n copies of the service running simultaneously and ensure that all updates propagate through the servers automatically. And there is a buzzword, Paxos, which is used to denote the consensus problem. How many of you heard of this? Okay, a few of them. A few of you. Okay. So actually, Paxos is a hard thing to do. We decided not to do it. And the reasons why, well, mainly there was a good paper by the Google engineers called Paxos Made Live. And they struggled a lot while implementing it. And actually, they came up with the custom modified version in Paxos, which is in fact unproven. It gave them a lot of pain and suffering during the operation of this Paxos. So we decided to stick with a simpler solution. A simpler solution would be just to replicate those updates which are coming to the state, right? So imagine if you have a log of what you're trying to do with your state. If you could replicate that log, you can keep the states in a synchronized manner. Well, eventually, as I become aware of, this idea was named Raft. And actually, we have reinvented the Raft. We were not aware of this algorithm. And Raft is another consensus algorithm which is becoming even more popular right now because it's simpler to understand. And well, if you're interested in this topic, I highly recommend you to read this paper. So, how Raft works in a few details, right? Well, remember our case that we have 3 master servers which have to be coordinated, right? What we do firstly is we elect the leader from those 3 machines. We elect the leader who is responsible to keep an update state and to coordinate in all the updates to those states. The leader should be backed up by the quorum who ensures that updates sent to the leader are saved, persisted to different storages in case of the leader fails. So timeline looks like the following. So if we have a time, we split time in a few terms. Every term starts with a leader election, which either results in a leader elected or not, where a leader may not be elected if the network partition in action right now. But usually election takes like less than a second, and a node with the most recent state becomes selected as a leader and starts to serve user queries. Well, there is a state machine. Well, yeah, so how the leader election is implemented actually. So every node on a startup starts with the follower state and eventually transitions to the candidate state because it times out because it has no active quorum. During the candidate states, it queries other peers and asks them either an active quorum at the moment and should I join it, or there is an election going on. So if there is an active quorum, a machine just joins this quorum of machines and keeps up with the updates. If there is no quorum at the moment, an election procedure starts. And the machine who wins the election, actually the machine with the most recent version of the state. So there is some versioning going on the state. So if you are thinking about how I can actually code it, you should also put some notion of state versions. And actually state version is determined by the term and the sequential number within these terms. So we use this particular scheme. We have a pair of 2 numbers. The first number represents the epoch, which is a term essentially, as the second number represents the consecutive number of the last update. So when the leader is elected, the second stage starts to operate. And what we are trying to do is to ensure that all updates are persisted to the logs on every machine and applied to the state only after the updates are persisted. So this is our goal. Oops. So how this works actually, when a client comes with a request to the state, we firstly persist this request to the changelogs and send the updates to the other peers. When they confirm that the change has been written to their changelog, we actually issue a command to apply this change simultaneously on the machines. And only when we ensure that the change is applied, we can reply back to user that this particular modification has been done. So the latency of this pipeline is about 15 milliseconds, I suppose. No, less. Well, about millisecond, I suppose. And the good thing that we can actually achieve a high throughput in this system by batching the log requests. So actually, if you think about the real network, it has a latency about the 1 millisecond. So if you would incur a millisecond latency in every request, then you will lower your throughput. So you can actually batch the changes within the packets in order to increase your throughput. And the most hard question in those distributed systems is how you should repair from failures. For example, what happens if one of the nodes fails, right? If the node failure does not lead to the breakage of the quorum, then everything continues to operate in ordinary fashion, right? So we can survive from one machine failing from those triplet, but if the two machines fails, then the quorum is gone and the system is not available. So when the failed machine comes back to the quorum, what happens is recovery procedure. And actually, a recovery procedure could be performed by replaying the logs. So this is done by just simply applying the locally stored records to the state, and then querying the active quorum on which updates have been committed during my recovery phase. So there is a catch-up phase when the follower, which is just recovered, trying to catch up the active quorum on the rate of the updates. Actually, to improve the recovery time and save the disk space, which is consumed by the changelogs, we can do a snapshotting to persist the state at points in time. Well, this is a regular technique for those of you who are aware of databases. Okay, so as I said, this works quite well in practice. We were able to achieve 100,000 updates per second. The failover time is usually determined by the heartbeat interval, which is usually a few seconds. And actually, the most funny errors are the timing ones. For example, we had a situation where the following trying to recovery was not able to catch up with the active quorum. So he was always a few changes behind. He could not participate in the quorum. And if you think about engineering this kind of system, you should be quite tidy, because engineering such a system requires from you a lot of attention to the details. For example, you cannot use, while performing your state update, you cannot use pseudo-random source of number generator. Because if those number generators would be incoherent between the machines, you would end up with two different states. So you have to ensure that randomness, the source of randomness, is coherent between the machines. And also, you cannot use the timing, because the clocks are usually unsynchronized between the machines. So usually, updates which require time use the leader time. So the leader, with every request, sends a timestamp when this particular request was initiated. Okay, so now I'm going on with table storage. Are there any questions to the moment? Okay, so the table storage, I remind you that tables are our first-class citizens. Tables are the thing we can split in every dimension we want. So in particular, we choose to split tables in vertical onto the columns in order to gain better compression ratios and read ratios from the columnar storage. So if you're following what's happening in the world around you, you may notice that Hadoop recently implemented something called Parquet, which is a columnar input-output format. Well, we have just a single format on how we store the data. So the data storage is completely covered by the system and completely hidden from the user. So user just worries about providing the data, and we ensure that we split it in an optimal chunks of data, compress them. Maybe if the user requires some column families, we split into the column families, and that's all. Well, Hadoop, in contrast, had a lot of input formats and output formats, and there isn't always debates on how we should actually store the data. And the people who are working in building the analytic tools on top of the Hadoop, for example, like Impala from the Cloudera or HBase, they are quite worried about the columnar formats. So that's why the Parquet was implemented. So we have those columnar-oriented storage from the ground up, so we kind of a few steps ahead here. Well, the other thing we have to worry about is how we provide the fault tolerance. There are two common approaches to the fault tolerance right now. First one is data replication, where you just keep several copies of data, and the second one is erasure coding. So we support both of them. Erasure coding, for those of you who are unaware, is a type of coding which allows you to recover from the erasure errors. So erasure error when a block of data is becoming missing. So why this matters? I'll try to explain a little bit. So if you store a table with a replication factor of k, then you incur a k times space overhead. So if your table takes 1 terabyte to store, then you actually occupy 3 terabytes on a disk. Well, erasure codes, like for example Cauchy-Reed-Solomon codes, allows you to obtain the same fault tolerance with a less disk space overhead. Well, in particular, if the Reed-Solomon uses nk parameters, which n is the number of blocks being encoded and k is the number of parity replicas, then you can tolerate k failures. Well, as a simplest example, you may think of XOR, right? So if you take 2 bits, you take XOR of them, then you have 3 bits, and if you store those 3 bits, you can recover either any of them by doing the XOR with the 2 remaining. So the problem with this erasure coding is that to recover the data, you have to do a lot of reads. So if you're trying to achieve the lower overhead of the disk space usage, you are, well, due to this formula, back on the slide, due to the formula on the third point, that the space overhead is k over n. If you're trying to achieve the better space usage, you are trying to increase the n factor, right? And if you're increasing the n, you are increasing the fan out of the recovery. So to recover a single block, you are required to do a lot of reads. And this is quite bad for the distributed batch-oriented system, because it means that the single piece of data you are storing would be smaller, right? Because you're chunking the data into the 12 parts, for example. So there is ongoing research on how we could lower this read factor. And actually, there is also a scheme called locally reconstructible codes, which is actually implemented by guys from Microsoft in the Azure storage, which allows you to have 1/3 overhead with just 6 reads. So basic idea is that you can store not the global replicas, which are computed from the all data blocks, but you can store so-called local parity replicas, which are basically XOR of the first 6 and 6 blocks. So this means, like in picture, you can recover a single failure in the first group by doing XOR of 6 reads, right? The same, you can recover a single failure in the second group by doing 6 reads. If you have more than 1 or 2 failures, if you have more than 1 failure, you have to use global replicas, but you still would be able to recover all the failures by doing 6 reads. So this just decreases the fan out of the recovery. So, any questions about the data storage? Okay. So the last point on scheduling. So scheduling is very different from what Hadoop does in our system, and there are reasons for that. So Let me cover it briefly. Well, first of all, there was this discrepancy on how we should, what would be the elemental resource we're scheduling. So both our historical and internal implementation in Hadoop uses the notion of slots. So slots are fixed per machine and actually corresponds to a number of simultaneously running processes. This does not really correspond to the actual resource usage, because your actual resources you're trying to somehow schedule are CPU cores and the memory, right? So we have an explicit notion of resources, and in fact we support both CPUs and memory. And scheduling is done by something called dominant resource. So if you would ever try to implement a scheduler, you would encounter the situation that you have to compute fairness between the processes. And usually when you have a single resource, you complete fairness just by that resource. So you compare the demands on the resources between the processes and then just normalize it by the fairness. In case when you have multiple resources, it's unclear which resource should be used to compute fairness. And actually, the resource being used is a dominant resource, which is relatively the highest demand. So for example, if the cluster has 10 cores and 100 gigabytes of memory, and the user requests 2 cores and 1 gigabyte of memories, then the relative demands are 2 from 10 by CPU and 1 over 100 for the memory, right? So the CPU would be more demanding, so it would be a dominant resource. And scheduling by the dominant resource ensures that there is a degree of fairness between users. So it prevents the situation when someone orders all the cores and none of the memory, and the other guy orders all the memory and no cores at all. So it still allows them to use cluster resources fairly. Well, there are also some differences between Hadoop and our YT scheduler, and mainly they are about how we think about the data. So in Hadoop, if you are aware of how Hadoop starts its own jobs, the entire task of producing data splits and actually fetching the data is up to the user code. So Hadoop actually, when performing the map reduce phase, either map or reduce phase, actually fetches the data by its own. And the Hadoop scheduler is completely unaware of those processes, and the data locality just being achieved by the hints from the client code. And we are trying to be more clever at this point, and actually we are asking scheduler to provide an optimal schedule for our own code. In fact, scheduler may communicate with master to understand where the data is situated in order to improve the locality in a fully dynamic fashion. So I think this is quite details for those of you who are not aware how the scheduling works, but the main difference is that the data is being pushed to the application in our setting, and the data is being pulled by the applications in Hadoop settings. This is always was a controversy between the Hadoop followers and unfollowers on how we actually should read the data. And there are benefits for both approaches. For example, if you push the data, you control the system more, and you can ensure more optimality. If you pull the data, you can do an efficient map side join, for example, or you can query external data during the reads. So, are there any questions on ideas of scheduling? Because I'm quite running out of time. So if you have any questions, this is a good moment to ask, right? Pushing the, well, this concept is preserved in both systems, right? So you see when the difference is quite technical. When you run the code on Hadoop, your code is being copied to the target machine, and when you ask in the copier to copy you somewhere, you provide some hints, and hints are actually taken from the HDFS with the locations of required data blocks. So when you read in the data, you issue a regular read request, and given the fact that most of the time you're scheduling on the hinted machine, you're reading locally. And in our setting, the algorithm is quite in reverse. So when a node with some data comes to a scheduler, the scheduler gives a job to a node. And scheduler actually gives that job that uses the data stored on the node. And when the node runs the job, the supervisor of the job just pushes the data within the job. When you allocate a job on a machine, you subtract resource usage from its possibilities. So when job is about to be scheduled, it has some demands on local resources, and the node has capabilities of running. So if there is a mismatch, then the job is not scheduled. Question? Yes, in fact, yes. So we do preemption, and the reason why we do in preemption is because there were situations when a single user came to a cluster, occupied the entire resources, and was sitting there for a few hours because no one had an ability to preempt it. Well, preemption, well, it's quite easy for the map tasks, and for reduce tasks, it's also easy. Well, there is no special about preemption. Okay, I'll briefly, in 2 words, cover the future plans, I suppose. We have a lot of future plans. We're trying to conquer the world. I'll briefly cover them in a few slides. Well, firstly, we'd like to improve our latencies and the data rates. There is a common trend in the world towards real-time computing, and this means, and this means that we have to be able to ingest the data at high rates, to buffer it on our own site in order to produce the optimal storage. And we also have to start thinking about how we can improve the latencies of data processing by either caching some pre-computed results from the previous map phases or something like this. So this demand is mostly driven by our customers who actually use this infrastructure, and they are not quite ready to move to real time yet, so this is just plans to the moment. And when they will become ready, we'll start to actually implement this. What happens with the slides? Okay. So the next thing we are trying to do is to scale within the data center. So as I mentioned, the scalability of current installation is mostly bounded by the amount of memory in a master server, right? And there is a good understanding on how we can overcome this. We can split the chunk management from the Cypress management into separate services on separate machines, and hence provide a layer of so-called metamasters. So those layers would just coordinate your namespace, your logs, transactions, and stuff like that, and actual chunk management for those group of machines would be handled by a set of masters on a lower level. So this would incur an extra synchronization between 2 layers, but we think it's worth it. We think this would allow us to scale to tens of thousands of machines. And actually the tricky part, which we not started to think about, on how we can shard the scheduling in this setting. I got it. There is a build out for those slides. Well, the other idea we're thinking about is how we can scale inter-data center. Well, the 2 understood demands for those kind of scalability are requests to keep data replicas in other data centers, because some processes may be working per data center fashion, or users just want to keep an extra replica in case of data center failure or whatever. And the other demand is to distribute data more evenly across data centers in case of archived data. A lot of data stored in MapReduce installation at the moment is not used in a daily fashion, right? Because they are mostly historical logs for a long period of time. And hence, you would like to be able to move this data between the data centers to free up computational capabilities. And the funny thing that actually, as far as I know what's happening in the world, no one actually knows how to do this properly. So there are some local solutions which handle either that particular case or that particular case, and the only maybe automated things could be implemented at Google, as far as I know, and we're trying to build something comparable for data management. there is another direction of our future plans, is to rethink how you tell the system what you're trying to do, right? So in MapReduce paradigm, you specify a mapper, a reducer, and a data set, and it runs a single MapReduce operation, right? So there is an ongoing, there is a popular trend towards the data flow programming, where you specify the data flow of your process, you specify the stages of an operation, and you just feed this computational graph to the system. And system actually keeps up the graph alive and running, handles all the fault tolerance, and does all by the magic things. So examples where this could be implemented are Spark, for example. Spark is an in-memory computational distributed computation platform where you actually feed a computation graph, and it actually saves you a lot of intermediate savings, so it's actually performance-wise efficient. And the related question would be to design probably a language for those data flows and queries. Well, I think that would constitute the most significant part of future plans. We probably would be dealing more with consistent databases, but this is unknown to the moment. And if you have any questions, I forgot to put my email on the slide, so if you have any questions following up this discussion, you can up to me so we can communicate. And if you have any questions at the moment, so I will gladly answer them. So I think at this moment my presentation is over, so thank you for your attention. Okay, so if no questions, then you're free to take a break. Thank you.